want to just say, I know that, I don't need to write it down, I'm okay with that too. Subtracting, you just subtract them. Multiplying, you just multiply them. Dividing is the one that takes a little extra because you have to make sure the denominator can't equal 0. So that's where your domain might change, and you might have to restrict some x values. We're going to do an example here in a minute that we're going to add, subtract, multiply, and divide, and we're going to talk about the domain and the range as well. It says, in each case, the domain of the new function consists of all numbers that belong to both the domain of f and the domain of g. It just means if your domain is restricted in one of those functions that you're adding or subtracting or multiplying or dividing, you have to take that in consideration when you put them together. And so we're going to just kind of see that you just kind of carry that domain over for the most part until you get to the quotient, and you might have to exclude an extra value there. Pretty straightforward, hopefully. People always get confused on these because they like to give you ugly functions in here that maybe you can't add together, or maybe you can't multiply together, like with square roots. Appreciate it. It means you just don't have to do a lot of work. It's really annoying when they give you like a trinomial and you have to multiply them out. That's a lot of work. So just know if you can put them together, you're going to put them together, and if you can't, you're going to leave them alone. Okay. For the people that are writing. Okay, let's go. Let's do a problem. That's what we're starting. So exactly what's on your homework is they ask you to add, subtract, multiply, divide. This is x cubed. There's a really small 3 there. So if f of x equals x cubed and g of x equals the square root of x plus 1, do the following. Add, subtract, multiply, divide. I picked one that was a little bit uglier just so that you would know that sometimes you can't do a whole lot with them. If they have like terms, you're going to put them together. If you can simplify it, you're going to simplify it. But on this one, if you're going to add x cubed to a square root function, right, f plus g is just going to equal x cubed plus the square root of x plus 1. I can't add a square root to an x cubed, which means that's it. That's the sum. If they were both polynomials, I could add them together, but on this one I can't. We'll come back to domain in a minute. Subtracting, same thing, right? You're just going to subtract them. And again, there's nothing that I can do there, so I'm going to leave it. Be really careful when you subtract something that has like a polynomial. Make sure you distribute that negative to everything. That's a common mistake that happens. This is really not very exciting. What happens when I multiply these two? X cubed times the square root of x plus 1. Can I multiply something outside of a radical and inside of a radical? No, which means I can't do anything here either. Kind of homework you hope to have, right? I used to pick different problems for this, where we actually had to work it all out, but then on the homework, when it gets ugly like this, people would freak out, so that's why I changed what I do. If I divide, I'm just going to divide. I don't know if in Algebra 2 you really talked about domains on here, but I want to talk about domain, because that's, I think, one of the big focuses of this first chapter is making sure you understand domains of functions. So let's talk about the domain of just f of x. X cubed. What is the domain of x cubed? Is there anything x can't be in x cubed? X can be anything, right? So the domain of f of x was all real numbers. What about g of x? As the square root of x plus 1. Square root functions never, well, rarely have a domain of all real numbers. There's always exceptions. Because I can't have a negative number under there. So what would my domain be for the square root of x plus 1? What's the smallest number I can plug in there? negative 1, right? Because that's what makes it go to 0. If you're still struggling with that, to find domain of square root functions, you just set the set what's under the radical greater than or equal to 0 and solve it, and you'll get that x has to be greater than or equal to negative 1, which means I'm going to say my domain is negative 1 to infinity. What does that mean for my domain of these sum, difference, and product? You just have to take any restrictions and carry them over. So A, B, and C, none of them can have a domain of all real numbers because they all have that same square root in them. All right? If f of x was also restricted, you'd have to kind of put them together and say, well, what would be the new restriction if they're both restricted? But on this one, this domain is just going to carry over to all of these. So the domain of this, I still can't have a negative under my radical, so it's going to be negative 1 to infinity. I still can't have a negative under my radical, so it's going to be negative 1 to infinity. And I still can't have a negative under my radical, so it's negative 1 to infinity. So on your addition, subtraction, and multiplication, for the most part, those domains are going to be the same, whatever the domain is when you combine those together. But the division is sometimes going to have a different one, because can I have the same domain on this one? Is it okay to say negative 1 to infinity here? Why not? Because if I include negative 1, I would now have 0 in my denominator, and I can't have 0 in my denominator. So I need to change my domain. What should that change to? Definitely I could plug 0 in there, but could I plug negative 1/2 in there? That would still work, right? That would give me a positive number over there. So I just can't include negative 1, but I can include everything up to negative 1. So how do I show that? It's just a parenthesis there, right? So that one, the difference here is I just have to exclude what actually makes the denominator equal to 0. So you might have to think a little bit on the division, especially if the domain and range is all real numbers for both f and g. If you put an x in the bottom, probably your domain is going to be restricted on the division one. So make sure you look at that. And on the homework, it says find the domain as well. So we don't really care as much about the range. The domain is really kind of the part we're looking at on these problems. Right? That's my only example of that because it's just adding, subtracting, multiplying, and dividing. Hopefully the domain stuff kind of makes sense. The other thing I want to talk about today is composition of functions, which was also in that same chapter that you did this in Algebra 2. I forget the chapter number, but composition is an operation, right? Just like adding, subtracting, multiplying, and dividing. And the symbol that we use for that is that little open circle. So it doesn't mean multiply f times g. We say that as f of g of x. And I always teach that is that open circle kind of just means like another set of parentheses. So that's the same as just saying f of g of x. F of g of x. Don't say f times g. Don't say fall. I always think of it as like you take the inside function and you put it into the outside function. You've been doing since middle school, you've been doing problems like this. Find f of 2, where you take 2 and you plug it into the function. Composition, you just take a function and put it into a function. Really important when you're proving that functions are inverses is that you have to do composition of functions. So let's just do one of these. Or maybe we could do f of g and g of f, maybe. To remind you that composition is not a commutative operation, which means that order matters. It matters which function you write first, because it tells you which function to plug in. I'm going to show kind of a lot of work on this, just in case you don't really remember how to do this. As long as you know what to do, you don't have to show me a ton of work. Some people kind of just jump right into it as you do this. So if I did f of g of x, I always just automatically rewrite that as f of what 2 means. That means I'm going to take g of x and put it into f. Or I always teach people that struggle with this concept, just start with the inside function. So leave f on the outside and replace g of x with what g of x equals, which is 2x. Right? So I just plug in g of x, which is 2x. Start with the inside function, work your way out. And now you do f of 2x, which means in the f function, everywhere there's an x, you're going to replace it with 2x. So I would get 3 times 2x squared plus 2. If there was more than one x in that problem, everywhere there's an x, I plug in 2x. And then you just simplify it. That would be 4x squared, so that would be 12x squared when I multiply by the 3, plus 2. Let's do g of f, just to remind you on the same one. Let's do g of f of x. So now f is the inside function, which is 3x squared plus 2. So I'm going to plug that into the g function, which is just taking 2 times 3x squared plus 2, which gives me 6x squared plus 4. It is not commutative. It matters what order you do it in. It's not multiplication. Composition. We talk about the domain of this, and the domain, finding domains of composition functions is a lot more complicated than finding domains of multiplication and addition, because it's this whole different operation. So I don't really stress it that much. If you want to talk about it, we can. If you want to read about it and go into it, you can. I don't stress about it because people just get really confused by it. It's really easy if the domains aren't restricted. Like, we could do this one really easily. What's the domain of f of x? It's a quadratic. It's all real numbers. What's the domain of g of x? It's a linear function. It's all real numbers. So guess what the domain of the composition is? All real numbers. But when you throw in rational functions or you throw in square roots, it's a little more complicated. So let me know if you want to know more about it, and I can show it to you, but I just kind of picked to say it's not that important. I've taken a lot of classes above precalculus, and doing composition domains not really the most important thing. So I let you skip over it if you want, but it is in your book, and I'd be happy to show you if you want to talk about it. I even might have a slide about it. Maybe, oh no, I took it off. Okay. But they talk about it in example 3 in your book. They can draw a lovely picture. But what I like to do is kind of making you think about taking a function and putting it into a function. So they call this decomposing functions. So you can think of like rotting functions on the side of the road. And so this one says, find f and g such that h of x equals f of g of x, which means they put a function in a function already, and they want you to break it apart as what 2 functions go together in composition to give you this new function. And some people just see it right away, and other people really struggle with this. For me, I always think about like the inside function and the outside function. So I'm always looking for something inside something else, like a radical sign, or like inside a fraction, or something all raised to a power. And maybe I'll make up another one here if we seem to struggle on this. Basically, I want to come up with what 2 functions could I do f of g of x, and I would get this out. I'm going to make the disclaimer here. You can't just pick one function as x, because if you pick one function as x, then the other function is always just that, right? See what I'm saying? Like if I said g of x equals x, then if I take that and plug it in here, because then you can just say, well, if I replace x with x, I get what I'm supposed to get. Right, that's cheating. We can't do that. So on the test, when I give you one of these, I'll have in parentheses, one function is not allowed to just be x. You got to think a little bit more about that. But do you see like an inside function here or an outside function here? Yeah, help with the first one. Like for me, the inside function, so is in something. So you see how this is like inside the square root? So see if this makes sense. What if I said g of x was x squared plus 5? What would be left as the outside function? Just the empty square root symbol? Can that be a function? And what would have to be there? What do we do when we have a x, right? Like the rule is you take the inside function and you replace every x with that. And so check and see if that works. If you took this function and you plugged it in for x up there, do you get h, which is the square root of x squared plus 5? That's not the only answer. There's lots of answers you can come up with, but to me there's always one inside-outside that you can think of. And they kind of set them up for you like that. So look, we're gonna make we're gonna call this 3a. We're gonna make this 3b. I'm gonna give you another one since I did that one for you. What if I said 1 over x plus 3 squared? Looking for the inside function to be g of x, and then what's left on the outside that you would plug into to be f of x. Anybody see anything on this one? And you can always check it. That's always the good thing that you can check on this. What do you think, Levi? So which one is the inside and which one is the outside? Because it matters, right? The inside is x plus 3. The outside is 1 over x squared. And again, think about if that works. If I took this and I replaced x with x plus 3, do I get back to this problem? Yeah. Anybody see another one that would work on this one? What if I just switched a little bit? What if I picked it up? What if I just did 1 over x here? What would the inside function have to be so that it would give me this? Instead of just x plus 3, what would it have to be? X plus 3 squared. See how there could be like a variation of answers there? A couple of those on your homework. I think it really kind of makes you think, because working backwards is harder than working forwards in math class. Try them. We'll talk about them. I like them. I like those kind of problems. There's also an example in your book about that, using decomposing functions, that maybe reading through it would make more sense if it's not making a lot of sense. For some people, it's always like, there's some things in math I feel like are very visual, and some people can automatically see the inside and outside, and some people really struggle with it. So if you struggle with it, outside function, like a square root symbol, right? That's an outside function. Anytime you see a fraction, right? Like 1 over something, the denominator can be the inside function, the fraction can be the outside function. Anytime you see a power, like what if I said like h of x equals x minus 3x squared to the 5th power? Anytime something's all raised to the power, like to me, that would break up as x to the 5th, and then the inside function is what's on the inside, which is x minus 3x squared, because I'm going to take all that and plug it into the outside function. So those are kind of big things to look for. Everything to a power, a square root sign, a fraction, Those are kind of outside functions, and then what's inside would be your g of x. So we'll see how we do on those. Okay, I got one more thing. Implicit equations, all right? Implicitly defined equations is kind of, again, kind of a calculus term. I feel like lots of things we do in pre-calculus, if you don't ever take calculus, you never get to see the reason that we do them. But an implicit equation is an equation that is kind of hard to solve for y, or the x's and y's are all mixed up. So it says two equations put together, most of them are going to look really weird. Mostly implicit equations are not functions, right? Like they're going to fail the vertical line test if you graph this equation. Like they're going to be weird kind of shapes. We're going to do a lot more with implicitly defined equations as we get further in this book, like next semester. But for now, all they want you to be able to do is tell me what these graphs are made up for. Figure out what are the two equations that make this up. And so the key idea there is we want to try to solve that for y, which sometimes is easier said than done. So when it says describe the graph, kind of what they're asking you to do here is see if you can solve this for y. Because if you can solve it for y, you're going to get y equals, and you're going to be able to see what kind of equations is it made up of, using one of those 10 graphs that we came up with. And so sometimes it's going to be really easy, like maybe you can just take the square root of it, or maybe you can just get y by itself very easily. I picked, yet again, a more difficult one, hoping that if we do a more difficult one, when you see an easier one on your homework, that it'll be easier to do. This one's kind of really hard to solve for y, because we have a y and a y squared here. So even if we like move the x squared over and factor the y out, like there's still another y hanging around, which means the only way I see that we can solve this is to think about factoring it. If you have x squared in the front and y squared in the back and some numbers in the middle, I think we could just like undo FOIL on this. Probably wouldn't be your first choice, but trying something else is not going to work on this. I've tried it. So if I undid FOIL here, do you agree to get x squared, I would just put x and x here? And to get y squared at the end, if you thought about foiling, it's really not hard to undo the FOIL here. To get y squared would just be y and y. And to get 2xy in the middle, what would I need my signs to be? Plus and plus. Okay, that's a perfect square there, perfect square trinomial. That's the same as saying x plus y squared equals 4. I believe the one on the homework is way easier than this because it's already in the squared format for you. So you get to kind of start right here as opposed to us having to go that extra step on the notes. But if we had to start right here, what would you say we should do if we want to solve this for y? What should be our next step? Square root both sides, and if you have a square, you want to square root it. So how does this made up of two equations, right here is how it happens. You get plus or minus here, right? When you take the square root of both sides of an equation, you get plus or minus 2. So to solve that for y, we would just subtract x over. And you get that it's made up of two equations, negative x plus 2 and negative x minus 2. So it doesn't even ask you to graph this. I'll show you the graph really quick if you want. But it says describe the graph. The graph is made up of two linear equations. Or maybe it's made up of two square root equations. Or you write like 2 of something. Negative x plus or minus 2. Just to show you really quick what that would look like. Y-intercept of 2 with a slope of negative 1 It'd be like down 1, over 1, up 1, back 1, right? That's a nice function. But also negative x minus 2 at the same time, which makes a y-intercept of negative 2 and a slope of negative 1. Did I do that right? That's weird. That's not exciting. The square root ones are more exciting. Those should be parallel lines. That might didn't work out so well. Alright, I think the one on your homework is like square root ones. Okay? So that's kind of a new word, implicitly defined equations. The directions don't say solve for y. It says find functions defined implicitly, which means you have to kind of know what the directions are saying, but if you know, it's not that much to do. So that's it. That's my notes for the day. So I wrote here, you do not have to do the domain of the composition of functions if you don't want to. If you want to look at it, if you want to talk about it tomorrow, we can. But I do want you to do the domain on 1, 2, and 5. This is why I kind of underlined those. But the rest of them, like when they say do domains on 16 and 18 and 19, you don't have to do the domains on those. But we can talk about them tomorrow if you want.